good. Yeah, hi everyone. My name is Andreas Lynge, and I'm a formal verification lead at Blockswap. And I need to put the mic closer so you can hear me. I have a background in math and formal verification, and currently specializing in formally verifying smart contracts. So what I'm going to talk about here is the Gateway Kernel, which originally was a project that we had about multi-chain ERC20 tokens, so transferring ERC20 token from one blockchain to another blockchain. And we wanted to formalize this, what we had done, but in order to do so, we decided to simplify the Gateway Kernel. And as it turned out, our simplification gave us a lot of new ideas, and those are those new ideas that I want to talk about here. And it's really a generalization of the multi-chain ERC20 token. Right. So first, what is a Gateway Kernel? It's essentially a communication interface of a domain, which is an execution environment, and so that you can think of it as a piece of state and some operations on the state. What it does is that the kernel is interpreting intents, and by what I mean by an intent in this context is that it's a partial transaction. We can think of it as a state transition in a state machine. And at some point, we're going to reach the end of the state machine, and we have fulfilled, we have a complete transaction. So what the kernel does is that it's performing a state transition from S to S prime, state S to state S prime on domain A. And then afterwards, as a reaction to this state transition that happened on domain A, we're performing a state transition T to T prime on domain B. And on top of this, we have this thing called the accumulator root, which is essentially it's a signature which is transferred from gateway A to gateway B as a proof that the state transition from S to S prime actually happened on gateway A. And yeah, so why do we need the Gateway Kernel? And that is to facilitate this communication. So facilitate communication of intents between different domains. And but the thing is that about the Gateway Kernel, we have it's general in the interpretation of the intents, such that an implementer of a Gateway Kernel can make a concrete instance and decide on the implementation of the intents. So concretely in Solidity, the intent interpretation is interface. So before going into the more abstract definition of the Gateway Kernel, I want to talk about the ERC20 instance of it. So here, Alice wants to. The abstraction here is that Alice wants to transfer 10 tokens to Bob, and in order to do so, she says it to the gateway A, and then what concretely happens is that 10 of her tokens is being transferred to the gateway, and now the gateway holds the tokens. Afterwards, the accumulator root is being provided to the transport layer somehow. This is not the job of the kernel itself. This is out of the scope of the kernel. And I will get more into the transport layer later. Then afterwards, Bob will say to the transport layer, I want to receive 10 tokens from Alice. And then the transport layer will forward this to gateway B, and then mint 10 tokens for Bob. So we have effectively what has happened is that Alice has lost 10 tokens and Bob has gained 10 tokens. And the job of the accumulator root here is to be able to prove that this Alice has indeed asked to transfer 10 tokens to Bob. Now, in the other direction, what Bob can say is that he wants to transfer 10 tokens to Alice, or it could be someone else, Carol. So what happens here concretely is that 5 tokens are being burned, and then Alice can say to the transport layer, I will want to receive 5 from Bob, and then transport layer forwards this to the gateway A, and Alice can get 5 of her tokens back by transferring 5 of the tokens that she earlier transferred to the gateway A back to her. But it could be transferred to anybody else. It doesn't have to be Alice, right? Another example of another instance of the Gateway Kernel is to provide loans, flash loans. So what happens here is that Alice wants to provide a flash loan, and then again she will transfer 10 ETH will transfer to the gateway. And notice that in this example we only have one gateway. And yeah, so the accumulator root can be accessed by the transport layer. Then Bob will be able to deploy a contract that is going to use the loan. And then Bob can go to the transport layer and say, I want to borrow 10 tokens, 10 ETH from Alice, and then please call my use loan function afterwards. Then the transport layer will forward this to the gateway, and the gateway will call the use loan function, and afterwards transfer 10 ETH plus maybe an additional reward to Alice. And so this in one transaction, Alice's loan can be borrowed by Bob, and potentially she will receive a reward. Yeah, and now for the general gateway. So what it looks like is that in general, so Alice is going to commit some intent F to gateway A, which is going to make some state transition S to S prime. And the accumulator root, so a proof of this state transition can be accessed by the transport layer. Then Bob will notify the transport layer, providing the same intent F as Alice committed before for verification purposes, and then also provide an additional intent G, which will be forwarded to the gateway, and then it will be this F, G state transition will happen on gateway B. Okay, the transport layer. So the transport layer is the one responsible for communicating the accumulator root from gateway A to gateway B, but it's only responsible for communicating the accumulator root. That's one of the important points here, is that is all it needs to take care of. It's not part of the kernel. It's outside the scope of the kernel. What the implementation of this transport layer is, or what it is. Some examples of it. It could be some kind of CK gadget, or an Optimism messaging bridge, or a hosted service, or you name it. Whatever you have as an operator of your concrete instance of a gateway, whatever you decide is acceptable in your scenario. And so one important point to make here is that it should be made so you make sure that the accumulator root is we only accept accumulator roots from this particular gateway. So, for example, we only accept accumulator root from gateway A, for example. But this is an implementation detail of the transport layer that often needs to be satisfied. Internally in the gateway kernel, the ingestion module is the one interpreting the intent for commit. And I'm calling it domain-specific intent here, because it's performing a state transition from S to S prime according to the intent of commit, and that this is parametric to the gateway. It's generic, so it's the implementer of the gateway deciding how the state transition, what should happen. And additionally, we have a dispenser module, which is similar, but interprets intent for execute. And making the state transition from T to T prime according to the arguments of execute, according to the intents given to execute. It is the accumulator is an index-sparse Merkle tree, and I will get more into details about the accumulator later. And it stores a sequential history of intents. So you can, whenever a commit has happened, you will be able to look up in what order did these commits happen. So the commit function of the gateway is what it does is first it will use the ingester module to interpret the intent F to perform the state transition. Then and then afterwards append the hash of the intent to the accumulator. And execute will take the F, the committed intent, an additional intent G, and then we'll use the dispenser module to interpret F and G to perform the proper state transition, and then append the hash of H, G to the accumulator. So examples of this is with the ESG20 example. So here F consists of an owner and a receiver and an X an amount that Alice the owner wants to transfer. So what happens here is that the X tokens from the owner is transferred to the dispenser module. That will be transferring it to the gateway. And then the hash of this is added to the accumulator. Afterwards, gateway B will be notified about this and will receive the same intent, an additional intent G, which is not being used actually, but it is there for generality. Other examples are using it. But what it does is that it will mint the tokens for the receiver given in the intent, and then append the hash of this to the accumulator. And now to the accumulator. So I said before, it's an index sparse Merkle tree, and I have an example over here, which is a small accumulator. And the accumulator can store 2 to the power x minus 1 elements, where x is the height of the accumulator. In my example, the height is 1, 2, 3. And so it can store 7 elements. For technical reasons, the last element cannot be filled up of the accumulator. The last leaf cannot be filled up. So in my example here, I have A, B, and C added, and you can add additional sequentially. You will add more elements to it, filling out the zeros for actual values that you want to store. So it is not. The gateway itself is not storing the entire it's not storing the entire tree here. It's only using a constant amount of storage space in order to do this, because x is a constant. Once the accumulator is deployed, x is a constant, and it uses space linear in x, so constant space complexity. And also the append operation is also constant time, and the membership proof checking is also constant time. The accumulator root up here almost is what we use to do the membership proof checking, and it's just one word which the transport layer needs to take care of. So it's very as minimal as we could hope for, I would say. Yes. So how does this work? So, for example, how do we achieve constant storage space complexity? So, say that we want to insert an element instead of the 0 here. Say we want to insert D. What we need to store? So, let me roll back up a bit and say how the tree looks like. So, we have transactions here, hashes of transactions here as the leaves, and the parent is always the hash of the children. So the parent of A and B is the hash of A and B, and the parent of C and 0 is the hash of C and 0, and so on. The parent of these two is the hash of these two, and all the way through in the tree. So now what we want to do is we want to insert an element here as D instead of 0. So the data we need for this is that we need to know C in order to compute this hash. We need to know this hash in order to compute this hash, and then we need to know this hash in order to compute this hash. That is why we only need 1, 2, 3, which is the height of the accumulator. That is how much data we need to actually be able to build this tree and maintain the tree. And what happens is that, so of course next time we want to insert an element, it's the data we need is different, but that is being handled internally in the accumulator. And then membership proof checking, also constant time, and that is just checking that you can get from here and up to there is a path from here and up to the root of the accumulator. That would be a proof of existence of C, for example. So let me just check how I am on time. How much time do I have? Good. So I want to just get into some more complex examples of what we can use the gateway kernel for. And in this example, I have Alice and Bob who are who want to they want to mute some state and then also provide some post conditions on the state, which is essentially saying that we will borrow the gateway this state as long as those that are using my state, these post conditions are satisfied afterwards. And then the transport layer will get access to the accumulator root, and then Carol will be able to come and say, I want to execute this transaction acting on a subset of the muted state that is located on the gateway. And then, so what happens? The bundle master's job is to execute her transaction using which may depend on some state from the gateway, and then afterwards make sure that the post conditions are satisfied. If they're not satisfied, everything will revert and nothing will have happened. But if it's satisfied, then Alice and Bob are happy because their post conditions are satisfied, and they may have made some money or something like that. So a concrete example of this is the loan again. So Alice will transfer 10 ETH to the gateway and require that the balance is at least 10 ETH after borrow. It could be like she wants to require that the balance is at least 11 ETH or something like this. But for this example, it's just she requires that it stays at least at 10 ETH. And then the transport layer will get access to the root. And Carol will then execute a transaction that borrows the 10 ETH, and then the borrower module here will make sure that after the transaction that there is still 10 ETH left, otherwise it will revert. And also afterwards, Alice will be able to say to the transport layer, finish the transaction by saying that, please give me my state back once it's done. So she will get her 10 ETH back plus potentially a reward. And in the end here, I want to also show that, my previous example here was state muting on a single domain. And we can actually mute state on a cross-domain basis as well. So what you would do here is that Alice and Bob, again, they will mute the state and provide the post conditions. Transport layer will get access to the accumulator root. And then the state is replicated on gateway B. Then Carol will perform a commit on gateway B, say I want to execute this transaction, and then it will check that the post conditions are satisfied after the transaction has happened, and that it will be transaction acting on the subset of the replicated state on gateway B. Now gateway B has, let's say it goes through, now the state on gateway B has been updated, and then the transport layer on the domain A, that the gateway A resides, will be notified about this, and the state will be updated accordingly on gateway A, so they are in sync, the state on gateway A and gateway B. And I think now, Matt, you want to come up and show us something that is a little more concrete than what I have been showing you.
Yeah. Stay there. So you're basically saying that you can mute the state on Ethereum and give it to someone else, and then they will execute it for you, right?
Exactly, that's what I'm saying, yeah.
That's intent, right? And you can write any kind of business logic around it. That's the generalized intent kernel says that. It's separate, but you can do a swap, you can do a specific action, or you can send it to optimism or anything. But how does it look like a user? So this is like something that we want to show you, like what the end user will get the value of this. You know, the current situation, like if we look for fast forward like in 8-9 months, you guess it's just like a kind of a conversation rather than transactions. You go to a chatbot and say that I want to stake. I just check all the things. It tells you, all right, your first time here, maybe it's the best way to go is this. You want to do it? Yeah, let's do it. And it will further checks the intent has been, it's just talking to you to get your intent in a more prescribed way, to get the script, to get the semantics, and how much you like to state, and say that you have $4,000 in your wallet. You can read it. That's pretty much everyone can read it. It's a blockchain information. You want to do 25%? Okay, I'll do it. And it's talk to the chain and just give this intents to execution, and voila. And you got something that you want to execute. Again, it's a blockchain, so it's creating an intent and approve. Boom. And you are staked your ETH with validator. So it's like more from a user perspective, it's changed the whole UX. When you can have very deterministic, expressive coordination between actors. So it's mute the state and allow the state to be executed in a different environment, but it rewards if it doesn't really execute and it comes back. So that's a guarantee. That's something that we're going to talk about in the next 10 to 15 minutes, what are the two components is basically making this happen in the on-chain, how we can have this kind of a sideline searcher market, MEVs can be executed in a get plus, but this is what the users will get it. It's a two-way street. No need to go. What is MetaMask? How do you connect it? What do I know? How many people know impermanent loss? Nobody. You talk about Dutch auction. It's a limit order. You don't know any limit order, but you can tell, and then they can make it for you. So it's like the world will come around the user with intents. And we would just want to show what an intent can bring to the user. The math is heavy, but experience is sweet. Thank you.